good to go. All right, cool. So we're going to talk a little bit about Erlang today, the concurrency model it uses called the actor model. And we're going to do a little bit of comparisons to Scala and just a touch of Haskell. So, all right, let's get started. So, about me, my name is Grant Williams. I'm a developer at Sequoyah Technologies. Like data science, functional programming, data structures, and algorithms, all that nerdy stuff. You can follow me on GitHub. It's pretty bad though, so that's just where I throw everything that I start and never get anywhere with. All right, so we're gonna talk about a few things today. We're gonna talk about Erlang, what it was for, what it's used for now. Just a general introduction to what concurrency is. There's a few misconceptions that people have about that. Some traditional approaches that a lot of the kind of older languages, like some of the staples like C, C++ use to concurrency. What Erlang does differently, talk a little bit about how parallelism is different from concurrency. Hit a brief overview of Erlang's virtual machine, the Beam, which I actually don't know what that stands for, but it's pretty cool. And then we'll talk about Scala and Haskell just a bit. All right, so the Erlang language was made pretty much exclusively for telecom. So it actually stands for Ericsson language. So Erlang language is Ericsson language. So, and it consists of two parts: the main language, Erlang, and then the OTP, which is the Open Telecom Platform. So when you download Erlang, you'll usually get these two parts. So Erlang runs on a virtual machine very similar to, the JVM or a lot of these languages these days. It's a functional language, but I actually don't think, from what I've read through some of the authors' statements, I actually don't think it was meant to be functional. I think they made it to work for telecom, and then the outcome of that was that it just was functional by design. And then, so it's distributed. It's extremely fault tolerant. And something really interesting about it is you can actually hot swap code in Erlang while it's running without breaking anything. So you can remove an entire system with a new one and then just continue on without even restarting it. And then it's got a really interesting philosophy where instead of coding for errors, you just let things break and then just ignore it and keep going. So it takes a while to get used to if you're used to some of these other languages, but it's very, very fun to use. So a little more about it. It's dynamically typed, but also very strongly typed, which is, for some people, kind of an odd combination. So it's types are inferred, but they are very much strongly inferred. So you can't mix and match like you can in languages like JavaScript. The data is immutable. If you set a variable x to 10, that variable x is 10. You can't add 1 to it. It's just 10. Once again, it's fault tolerant. And then Joe Armstrong, the co-inventor of Erlang, described it as if Java is write once, run anywhere, then Erlang is write once, run forever. So the whole philosophy of this language is to work with the telecom industry and then to allow errors to not propagate through the system and just keep going through anything. High uptime was the most important feature of the language. So let's talk a bit about the fault tolerance of language. So the whole point of the language when it was designed was to minimize the impact of errors and to really allow you to recover from them quickly. So if something breaks, then the system basically will just get rid of that process and then try and start a new one and keep going. So it encourages a different style of programming. So instead of trying to catch errors as they happen, you pretty much just ignore them and then keep going. So you program with the assumption that I'm a great programmer and I'll make no mistakes, and then you let the language catch all those mistakes that you end up making. It's pretty interesting. It's got process isolation. So the main use of Erlang, you can run it serially, but when you run it in concurrent systems, each process is completely isolated. And then larger systems, that's kind of built up the stack. So larger systems are usually pretty isolated too. So you can have a whole major system go down, and the rest of the program will keep running. So it's pretty wild. It's pretty fun to learn too. So the biggest thing is that hot swapping code was really big for them. So you can upgrade code just on the fly in production with no problems. So without restarting or interrupting. So let's just look at a quick example of Erlang. So the syntax is pretty different from what you would expect from a lot of these modern languages. It was made in 1986, I think. So it's a functional language. So you'll see here, this is just a classic Fibonacci function. So it's got pattern matching. So when you define a function, it actually looks at what's inside of the parentheses, the variables or the parameters, and it matches your function call based on that. So these are all 3 different functions that share a name, and then depending on what's passed into the function, it'll choose which of the 3 to call. So, and then return statement in Erlang is a period, which is pretty different. So, but you can see it's pretty easy to understand syntax, a little weird to get used to, but pretty legible. All right, so let's talk about concurrency. So concurrency is the ability of a program to work on a lot of different things at once, but not necessarily at the same time. So maybe you send out a request, and while you're waiting for a response from that request, you're working on something else. Then you get that request back, you pause what you were working on, handle the request, and then go back to that. So it's really important to know that concurrency does not always equal parallelism, but they can be used together. So we're going to talk about 2 big approaches to concurrency today, and then a few variations of the actor model. So the kind of classic approach is using threads with locks, mutex, semaphores, things like that. So let's talk about that. So C++, for example, is a really great language that has strong use of threads and locks. And now I'm not going to claim to be the best concurrent C++ programmer, but I will say that almost every time I have done something concurrently in C++, I've wanted to punch my monitor. So they're difficult because sometimes you don't know what's wrong until it's in production. All right, so for threads, each thread is given a task, and then it attempts to work on, for example, a shared memory space. And then a lock is to guarantee, or a help guarantees, so that you don't have 2 threads that are changing, say, an array in 2 different places at the same time when they're not supposed to be. So you use these locks to prevent threads from overlapping tasks and then just mangling your data and giving you just a bunch of garbage. And locking's really complicated. We're not going to go too much over it today. There's 2 general approaches to locking, popular ones at least. And you either need atomics, which a lot of times now are actually implemented at the hardware level. I realized I didn't know that until recently, so that's pretty cool. So atomics just basically guarantee that you're not accessing the same like memory space at the same time with 2 different threads when you're not supposed to be. Or you can use an algorithm like Decker's or Peterson's algorithms. I was going to go over them. They're pretty complicated, so they're not anything crazy, but they're not necessary. So some disadvantages to threads and locks: they don't compose well at all. So when you have locks, and then you need those locks to work inside of a different part of a concurrent system, then you need locks, and then every single lock has to know about the other locks in your system that might affect it. So it makes encapsulation super hard. They don't really compose well. So scaling with threads and locks is really difficult, and you have to be very careful with what you're doing or you'll break it. It's also hard to know, do I have enough locks? Do I have too many locks? Is the order that my locks happen correct? When I test it and I think that they're correct, and then I push to production and then something happens I didn't think was going to happen, what's going to happen to my code? How do you handle errors with locking? And so these are all pretty tough problems. A lot of the languages have some nice built-ins to help you with that, but at a conceptual level, I don't think it's the ideal approach. Then, so this is just some pseudocode that we're going to go over. Rip this straight from Wikipedia. So up here we have an account class that has balances, and then you can withdraw or deposit. So this would be a serial method down in the middle that would transfer. So you would take from an account to an account and how much you want to transfer. And so serially, that's pretty easy. You just move from one account to the other. And then with a lock, you need to have some sort of ordering for the locks, and then you can do them one at a time. And the part of the problem is, like, how do you decide which transfers need to go through first. Is there, you need some kind of bookkeeping to make sure that you're not withdrawing from an account that was supposed to have something deposited in it first, and then giving the user a huge fee in their bank because they've overdrafted their account even though they should have already had money in it. So this is just a quick example of that. So let's talk about the actor model. So it was proposed by Carl Hewitt in 1973, and the basic idea of the actor model is that every process is completely isolated, that it's really easy to make a process, they're super fast to spin up, they're lightweight, usually in kilobytes or less, and they're super easy to destroy. So they have no shared memory at all like threads, and they only can communicate through message passing. So the only way you can get actors to talk to each other is through a direct message from actor to actor. And because they have no side effects, they work fantastic with functional languages like Erlang. So the use of actors is a little bit different from maybe what you would use a thread in C++ for. So concurrency in Erlang, if you have a lot of calculations that are heavy on math, you don't want to use concurrency in Erlang, really. It's not going to speed up the process a lot. It's more for message passing or doing a bunch of tasks, whereas threading in C++, you can increase computation time quite a bit by doing computations on multiple threads. So Erlang's was made for the telecom industry, so it's a little bit of a different design choice. And then in Erlang specifically, all of these actors that make that are made can die or be recreated just kind of at will really easily without affecting anything else. So the way the Beam VM actually handles this, the virtual machine that Erlang runs in, is an OS thread is used to make a scheduler, and then that scheduler makes actors, and then you can have maybe 100,000 actors on a single core, and it's fine. So the virtual machine actually has a preemptive scheduler, so it's able to kind of tell if one of these tasks is going to hang the whole system, and it'll preemptively stop it if it goes too many cycles, or if it receives a statement but there's no message in it. And then it also kind of has I wouldn't say a guarantee, but it attempts to guarantee fairness across these actors. So when you have a whole bunch of things that need to be done, it does a pretty good job of balancing it across them. All right, so why does Erlang use the actor model? Because it was made for the telecom industry, it was primarily used for brokering or message passing. So you can think of it as, for example, calls. So you want it to be very easy to add a phone call or to drop a phone call from your system. And if one phone call dies, you don't want to throw an error that just drops everyone's phone calls across the system, or you're going to have a lot of upset customers. So they made it really easy for these, for example, in this case, phone calls to be added or dropped. And then they use very little memory so that you can have a whole bunch of them going on at the same time, because they're not doing a lot of strong calculations. They're mostly just passing information back and forth. And then Erlang's fault tolerance, one of the little mottos they have is that failure is a feature. So you can have these failures right in the system and not worry about it. So let's talk about an example using Erlang. So it has a lot of really great built-in support for this. So you just need to make a spawn, which is it's the scheduler that will create the actors for you as needed, and then you can send messages. So Erlang doesn't have loops because it's purely functional. So down here we just have a little recursive send message here that gets caught up here. So each message sent, it'll just increment by 1. So you can see down in the comments below, it might be hard to read, that you basically just call counter run, and then it'll count the value up to 100,000. So it's a pretty straightforward syntax. Might take a little bit of time to get used to, but the magic's happening right here in this receive message. All right, so originally the Beam virtual machine was concurrent, but it wasn't parallel. So doing complex tasks might be slower concurrently than doing them in serial. But in 2006, they updated the virtual machine. And the craziest part is they were able to update the virtual machine without changing the language at all or having side effects. So it was kind of like black magic for all the users, but I'm sure there's a lot of tough work that went into that. And they added symmetric multiprocessing, which allows Erlang to be concurrent and parallel. And the only thing you have to do to allow that is to put on a tag -SMP, and it'll automatically make the processes parallel. So for the new virtual machine, each scheduler, or it has multiple schedulers, and it assigns each scheduler to an OS thread. So if you have a quad-core processor, it'll automatically spool up 4 schedulers, and then each of those schedulers are able to create actors. And then, but it's really important to know that the actors themselves, never actually are parallel. They are still completely isolated. They don't do any kind of shared memory, and they still only use message passing. All right, so we're going to do a little bit of a deep dive into the virtual machine here. Before 2006, it was that single scheduler always, or if you wanted to run multiple, you would have to spool up, basically like running different applications to do any kind of parallel work. So now on the new machine, you only have to use the multiprocessing flag, and then it'll automatically parallelize the work for you. And it uses a common queue, so all of the actors that are made by all these schedulers are all put together, and then as the scheduler is able to do a task, it'll grab from the queue together. So it's distributed pretty evenly across the cores, which is really nice. So if you have some of the cores with much harder computational tasks, one of the schedulers might be doing that, then you don't have to worry about one core at 100%, all your other cores at like 2 or 0. So it has a tiny bit of overhead for using the parallel version, but not very much. And ironically, the virtual machine itself actually uses locks underneath. So even though I was trashing on locks earlier, you do need them for the virtual machine to work. So, but because of that, sometimes the locks will slow down your code. So if that's the case, you can actually have it run multiple copies of the program. So in each program, we'll have one scheduler instead of having one program with 4 schedulers, for example. All right, so let's compare this just a little bit to Scala. Scala is a strongly and statically typed language, and it has a very advanced type system. If anyone came to the talk last month, I believe we went over that. So it has an actor model that can be used in the Scala actors library. I think it also has another approach to concurrency, but I'm actually not sure. So it has 2 kinds of actors. There's thread-based or event-based. And thread-based actors work on JVM threads, so they're kind of more like what you would see from like a C++ thread. They're really, really great at doing complex calculations or doing I/O that you don't want to be interrupted. But they're heavy. They have a large overhead with the scheduling. But because they primarily should be used for calculations, you shouldn't notice them if you're using them correctly. So if you're doing a bunch of matrix operations in Scala for some reason, then you're not going to notice the overhead from spooling up the threads. And then so the actors actually block once they're in the receive block of the code, which we'll go over in just a second. So they'll block until they get a message. So they are blocking, unlike Erlang. But Scala does have an event-based actor, which is very, very similar to what Erlang uses. So they share threads, and they use messages to interact with each other, much like Erlang does. So they'll share one JVM thread, which is kind of like the OS thread, and Erlang will have 10,000 actors on it, and that's fine. And you won't see much of a performance loss there. And because they are message passing only, they'll never block, and you can have them spool up or die, and it'll be okay without breaking other parts of the program. They're very lightweight, and the big difference is they use a receive, or they use a react instead of a receive block. So Scala is pretty cool because you kind of have a mixture of that C++ style threading with the Erlang actor-based, or not actor-based, but messaging-based. So this is an example of the JVM style threading. So you can see here that you make a counter class. This right here, the receive, means we're going to be using the thread-based actors instead of the message-based. And then down here you can see you loop and then increment in concurrently. So finally, we're going to talk a little bit about Haskell. Oh, yes.
Before we move on from the Scala, there's a library on Scala called Akka,
Yeah.
which implements basically all of the functionality of Erlang's OTP library on the JVM for both Java and Scala.
That's very cool.
And it has the supervision hierarchies that Erlang has on its actors, and it uses the event-based.
Okay.
The Scala.actors package is pretty much deprecated and been removed from the Scala library.
Okay. Yeah, I didn't realize that. See, I don't do any Scala coding, so I was just looking at documentation to see how they're different. So that would be it. So that's very cool. I'll have to update this sometime with that. Then Haskell's one where I also haven't done a lot of concurrent programming, so this is from their documentation primarily. So Haskell is very similar to Scala. It's strongly typed, statically typed, and also has a really advanced type system, has, algebraic types. And then Haskell has concurrency and parallelism, but it keeps them separate. So kind of like the threads versus messages of the Scala actors library. So for concurrency, it uses software transactional memory, which is, it's actually a really interesting model. So that it has shared memory for threads, and threads write to the memory assuming that they're going to be able to write to that memory location without a problem. And then they log the changes that they made. And then when it's time to finish the calculation, the changes are validated. And then if those changes didn't have a conflict, then they're committed. So it honestly sounds almost exactly like what you do with your Git code. So you push it, you hope it's okay, and if there's some kind of merge issue, then you can't commit and it has to be fixed. So the way Haskell works on fixing those merge issues is it actually just kills the thread and restarts the process and then sees if it can finish it then. And then if that doesn't work, it gets complicated. So these can have a pretty high overhead actually, but if you're using them for like message passing, they're great. And then Haskell does parallel processing using something called green threads. So it's kind of like the SMP implementation of Erlang or the JVM thread implementation of Scala. It's a many-to-one mapping. Haskell threads, like you can have maybe 10 Haskell threads to an OS thread, for example. It's really great for doing complex calculations like math. Errors are really rough with the threading in Haskell. It kind of goes back to the problem with errors and locks in C++. One way you can get around this is you can use monads. They are pretty useful in minimizing the amount of errors that you would have and the code touching each other. And then finally, Haskell's parallelism doesn't distribute as well as Erlang's does. So Erlang by default will use however many cores your computer has unless you tell it otherwise, and it'll assign a scheduler to each one automatically. And in Haskell, you kind of have to do it yourself. So you can't just throw it onto a cluster with a bunch of CPUs and let it do its thing. You have to actually know what you're doing a little bit. All right. If anyone has any questions, I would be happy to take them now.
What have you built with the actor model?
With what?
Have you built anything with the actor model?
Yeah, so I actually I've been working on just a little fun app to learn about systems. So I've been working on a messaging app. So I built the broker that handles the communication between the front end and back end in Erlang, and that's actually how I found out about Erlang. It's a real treat to build brokers with. It's real easy. I made one in Python for work, and it's not as fun. So just works really well for what it was made for. It's kind of a niche language, but if you want to do message passing or brokering or anything like that, then it's fantastic. If you want to show off on HackerRank, you can use Erlang too. There's like 7 people that use it across the whole website, so you can do that. Yeah?
How
Yeah. So, oh, sure. So the question was, RabbitMQ is implemented in Erlang. Are there any other similar bits of software that use Erlang? So probably the biggest one that most people would know is WhatsApp is written primarily in Erlang. So it's a messaging app that got bought out by Facebook for like, I don't know, over $1 billion, I think. And their main programming language is Erlang. So a lot of these kind of programs where you're just passing information back and forth, or like, for example, RabbitMQ, it's basically a broker between systems. So it's another great use case for Erlang. So I think there's another messaging queue out there that's in Erlang, but I can't remember off the top of my head. And then there's some stuff in Elixir, which is basically Erlang.
CouchDB is written.
That's right. Yeah, there's a few database management systems, I think, in Erlang too, but I don't know how much they've caught on, so some of them probably more popular than others. All right.
What would be a use case for
Oh, yeah.
just Erlang? So like Scala has libraries that are very similar,
Mhm.
and Elixir is basically like a wrapper around TP. What would be the use case for just Erlang?
So Erlang's probably not the best general programming language because it has that VM it uses, and it's kind of weird because it has a VM, but it's also compiled, so it's kind of a strange setup it's got going on. But a good use of Erlang is if you use the Phoenix framework, which is written in Elixir. Anytime you write code in Elixir, there's like a 50% chance you're gonna touch some Erlang. Like they're just so connected that you might do a little bit of fiddling in Erlang with Elixir. So I would say primarily just because Elixir is pretty popular that might use a little bit of Erlang.
So basically, if you use Elixir and have to modify the beam, then you would need to know it.
Well, you won't have to touch the beam because the beam is, I don't know what the beam is written in, probably like C or something like that. But a lot of the libraries that you would use in Elixir are going to be a mixture of, Erlang or Elixir. You don't really know. It's kind of like how Scala and Java integrate so well that you can have programs that have Scala libraries, Java libraries, just kind of dependent on what you're doing. So Elixir has a lot of nice like syntactical sugar on top of it. It writes a lot like Ruby, reads like Ruby. So, and strings are garbage in Erlang. So use Elixir for strings. Strings and like binary and everything is all the same. It's just all arrays, and it's gotten better, but it's not great still. Oh, and the last thing is binary is really interesting in Erlang. So you can use like a lot of people use binary as like message IDs and things like that. It handles it just really elegantly. So it's great for assigning like PIDs or whatever. So it's another useful thing about Erlang or Elixir. Yeah.
If strings are garbage, how bad is Unicode?
To be honest, I just haven't looked.
I don't think Unicode is the look. I don't think
Yeah.
Unicode was invented when Erlang.
No, I don't think so.
Exactly. So how bad is it? I mean,
See,
to
that's something I'm gonna have to look into one day since I'm writing a messaging app. But I might have to mess with that. So, but right now I'm just going with we'll deal with it eventually, and maybe Elixir does it better. I haven't actually looked. I'm hoping so. So I have doubts though, so we'll see.
I'm sure ignoring Unicode in 2018 is a good idea.
Yeah, that's what I was thinking too.
It's just bad.
All right. No online questions, right? All right, cool. Well, I think that's it.